Hello everyone, in this video we're going to discuss satellite circular motion. By the end of the video you should be able to be confident solving problems with speed of the satellite and Kepler's third law. Alright, so let's talk about how to derive the speed of a satellite. So let's say we have a planet right here and there's a satellite that's orbiting the planet. At this point we know that there is some F big G force due to gravity, and that's the only force acting on it. So in this case, since that's the only force, the F net is going to equal F big G, which, because we're moving in a circle, the net force is going to be the centripetal force. So F centripetal is equal to this Fg. And so we have an equation that solves for centripetal force and for this F big G. So if we solve those in, we have the mass, which in this case for the centripetal force, this mass is going to be the mass of the satellite. And we'll call that m sub s, and this will be the mass of the planet. And then we have the velocity squared over the radius. So this radius would be like here to here is the radius. Okay. And F big G is the gravitation constant, mass of the planet, mass of the satellite, over the radius squared. And so the mass of the satellites cancel, one of these radiuses cancel. So then we get v squared is equal to gm mass of the planet over r, and we can take the square root of both sides and get the velocity as gmp over r, and this will be of the satellite. So this will be a common equation that you'll probably want to use. You may want to memorize it, but I would recommend understanding how it's derived. So if you do forget it, you can always set up a little mini problem for yourself and solve for it. So let's do an example using this equation that we just found. So it says the satellite orbits a planet at speed v, and a second satellite orbits the same planet in a circular orbit at a speed of 2v, and then we're going to compare the satellites' periods. Okay, so we just drove the equation for the speed equals the square root of g mass of the planet over r. Now you may be thinking, we don't have anywhere in here with the period, so how are we going to get that? Well, we know that we have a different equation for v. And the v that we have is the tangential speed, which in general just equals 2 pi r over the period. And note that these are circular orbits, so we can use this circumference of a circle in our tangential speed. If it was not a circular orbit, you'd have to do something else. But we can use this equation, which will derive our radius, so we can multiply t and divide by 2 pi. And we get that the radius equals v period over 2 pi. And so that's our radius. So now that we have the radius, we can plug in this radius back into our equation. You could also set this equal to the equation and then solve for it, but we'll do it this way and see what happens. So we have this, we have gmp over this radius, which is vt over 2 pi. And so if we go ahead and divide this fraction into this fraction and simplify it, we get that the velocity equals g mass of the planet 2 pi over vt. And so now we can square these both and get the velocity squared equal to gmp 2 pi over vt, and multiply this v over and get you would get v to the third equals g mass of the planet 2 pi over t. And so this is kind of our final relationship. So this is our whole equation, but we are only comparing the speeds versus the period. So we can go ahead and figure out what this proportionality is. So using this equation, we can say that the velocity to the third is proportional to 1 over t, And so this will also be true that t is proportional to 1 over the velocity to the third. And so if we say, let's say the period of the initial satellite, or satellite 1, is just t1, and the speed v1 is equal to v, and then period 2 is v2, which equals 2 times v. So t1 is simply 1 over v to the third, because v1 equals v. And so if we wanted to find what v2 equals, we could say t1 is proportional to 1 over 2v to the third. And if we take this out, we would get 8v to the third, which equals 1/8 v to the third, or not, 1/8 times 1 over v to the third. And so we know that 1 over v to the third is proportional to just the original t, and this should be t2 also. We know that this 1v just is proportional to t, so we can say that t2, or the second period, is 1/8 of the other period, which makes sense. The second period is shorter than the first period because it's moving faster, and the period is just how fast it takes to get around the planet. So that would make sense. Alright, lastly, let's talk about Kepler's third law. So the Kepler's third law relates the satellite's period and radius of the planet. And so we kind of just used that a little bit with period and velocity, but now we'll talk about the period and radius. So I'm going to go ahead and derive this equation so that you understand where it comes from. So we have the velocity of the satellite is equal to the velocity, like the tangential velocity. So these two are the same thing, but we have two different equations that we could use. We have the square root of big G mass of the planet over r equals the 2 pi r over v. So we kind of use the same strategy in the last equation. And so now we just have to derive this equation for t. So we can square, or this should not be v, my bad. This should be a t. This is the period. So we used this in the last equation. So now we can just square both sides. And because we don't really want the square root in the equation, that's why we'll square both sides here, so that we can just get pure terms and relate the radiuses together, because we need these radiuses to be one variable. And so now we can multiply by this r and get GMP equals the 4 pi squared r squared over t squared. Actually, no, this should be a squared r, sorry. And then we multiply this r, so this becomes r to the third. And so now we can move this t to the other side and get t squared GMP equals 4 pi r to the third. That's a nice arrow there. And then we divide over and we can get t squared is equal to 4 pi r to the third over GMP. So that's kind of our, that's the whole equation. So you may see it written out more with like this saying the same thing, but just denoting that this is the relationship between the two. And so this t squared is proportional to the radius of the third. So you could be asked a question saying, like, if the radius changes by this amount, how much does the period change, or vice versa? And you can use this proportion to solve those without having to do this whole derivation. So yeah, you should be able to solve really any equation involving period and radius. Alright, so if you have any questions, feel free to leave them down below, and thank you for watching.